Welcome back. So we're in the middle of thinking about binding from the point of view of statistical mechanics. And just as a reminder as to why we're making this detour in the middle of thinking about biological dynamics more generally, the idea is that I want to be able to write down some more general dynamical equations that involve a more nuanced treatment of binding. And one of the key ideas that we need at this point is cooperativity. So last time, just as a recap, we thought about the single ligand receptor problem from the point of view of statistical mechanics. And the protocol for statistical mechanics told us that we needed to do four things. We needed to identify the states, shown here. And I argued that there's only two categories of state. There's either the empty state, shown here, or the bound state. So there's two categories of states, and that's it. In other words, once we've acknowledged that either the receptor can be empty or bound, there's nothing more to say other than the degeneracy of all the ways of distributing those red molecules on the lattice. So step two is we compute the energy. And note that when we start out with L receptors in solution and none of them are bound to the receptor, L ligands in solution and none of them are bound to the receptor, then the total energy is called L times the solution energy. And that solution energy is a parameter. You could think of it like putting a molecule of oil in water. There's some free energy cost associated with doing that. Then when one of the ligands binds to the receptor, as shown here, then what happens is that we actually now only have L minus 1 ligands left in solution, and one of those ligands is bound to the receptor. So that gives us an energy epsilon B. We next compute the multiplicity. That's the number of distinct ways of distributing the L ligands in solution. And note, this is really super powerful, and it's not naive. This is actually deep, because this is where the statistical mechanics power reveals itself. Why? Because instead of sitting around and thinking about every possible state of the system, we actually have a way of capturing all of them at once. And by virtue of that, we can ignore the solution. Once we've acknowledged this multiplicity, we can ignore the solution. The final step is we compute the statistical weights, and we note that the statistical weight is the product. So we multiply multiplicity times the Boltzmann weight. Okay, I can't write it here, but we multiply multiplicity times the Boltzmann weight. And then with that, to get the probability of binding, we take this as our numerator, because that's the state of interest, and then we divide by the sum of these two different weights, which is sometimes known as the partition function. So it's the sum over all of these states. So that's what we do. We divide by the sum of the statistical weights of all the different states, and that's the so-called partition function. So that's what we did last time. So now what we're going to do today is in this vignette, I want to consider a different problem, which is a receptor that has two binding sites. And here this is just to show you the cartoon. I'm going to draw my own version. But bottom line is we have this receptor. It has two ligand binding sites. And what we need to do is we need to carry out the injunction of the statistical mechanics protocol. So once again, let's go up here and actually do some copying from what we did earlier. So I don't have to redraw everything. So we know we're going to do the states, weights, copy. So we know we're going to do this statistical mechanics protocol. Let me go up here and grab one of my little diagrams, so I don't have to redraw it. Copy. Okay, so I'm going to paste this here. Let me do a little bit of surgery on the receptor. So this time our receptor has two binding pockets. And once we've got that, I'm going to just paste it 4 times. Oops. Sorry, you're going to have to bear with me. I screwed up. Why? Just a sec. So I need to copy this. Yeah, that's better. And I have 4 states of occupancy. So in this state, the left-hand guy is bound. In this state, the right-hand guy is bound. And then in the final one, both of them are bound. Okay, so we have 4 states, right? So the reason I say we have 4 states is that the receptor, it has 2 binding pockets. The receptor can either be completely empty, which is shown at the top. There can be 1 ligand bound, so that's the 2 states in the middle, or it can be doubly bound, and that's shown at the bottom. So once again, the energy is L epsilon solution for the first one, L minus 1 epsilon solution plus epsilon B, L minus 1 epsilon solution plus epsilon B. I'm assuming that this is a homodimer, so those 2 binding sites are equivalent. And then finally I have L minus 2 epsilon solution plus 2 epsilon B plus epsilon int. And that's the key point. The key point is that I've now introduced here a cooperativity energy. What I'm saying with this cooperativity energy is that when both the ligands are on the receptor, that the total energy is actually lower than just 2 epsilon B. Meaning I actually, by virtue of having them both bound, if you like, there's an interaction between the 2 of them through the receptor that leads to a net lower free energy than the sum of the 2 binding energies. It's super important. Okay, I'm going to just by scratch and sniff write down all these multiplicities. So this one, so this one is omega to the L power over L factorial. This one is omega to the L minus 1 over L minus 1 factorial. This one is omega to L minus 2, L minus 1 over L minus 1 factorial. And then the last one is omega to L minus 2 over L times L minus 1. No, I didn't do that right. I'm going to call this L minus 2 factorial. Okay. Now, I want to talk about, I've already mentioned the Gallery of Prisoners of Michelangelo, how much I love that. It's the entrance hall to see the David in Florence. And the reason I like the Gallery of Prisoners from Michelangelo is they're a statement about potential. They're unfinished statues, and there's the potentiality of human creation there. And that I find both beautiful and inspiring. But I also think of it as being useful for us when we do mathematics, because when we have expressions, often they invite us to be clever and to try to find ways to simplify so that we don't have such a mess. And so what I'm going to do is I'm going to, right here, I'm going to redefine my zero of energy. Okay, so if I redefine my zero of energy to be this L epsilon solution, that means that here the energy is going to be 0. That means that here the energy is going to be epsilon B minus epsilon solution. Same for this one. And the bottom one is going to be 2 epsilon B minus epsilon solution plus epsilon int. Now, why am I telling you this? Because I'm telling you this because we have the freedom to choose our zero of energy. And like in the Gallery of Prisoners, this thing is potentiality. I want to make moves on this chessboard that are gonna make my life as easy as possible. So why do I want to carry around this L epsilon solution if I can, from the get-go, um, set it equal to 0 as my reference energy? And I can similarly multiply all of these weights by the same quantity. So I'm going to do that. What do I mean by this? I can always multiply statistical weights as long as I multiply all of them by the same quantity. Um, then that changes nothing, because you'll recall that the probability of a given thing is the statistical weight, the net statistical weight, divided by the sum over all of them. So if I've multiplied them all by a common factor, that common factor will cancel out. That's really nice because this leaves behind 1, this leaves behind L over omega, this leaves behind L over omega, and this one leaves behind approximately L squared over omega squared. So that's what happens if we adopt this simplification. And so the statistical weights are 1 L over omega e to the minus beta delta epsilon. I'll say what beta is in a moment. L over omega e to the minus beta delta epsilon. And then this last one is L over omega squared e to the minus 2 beta delta epsilon plus epsilon int. Beta is defined as 1 over kBt. Delta epsilon is defined as epsilon b minus epsilon solution. Okay, so that's a lot to take in. Most of it is cosmetics. Most of it is beauty. It's not fundamental. So just a reminder, what we've done is we've exploited the statistical mechanics protocol. How have we exploited the statistical mechanics protocol? By essentially following the edict that we need to identify the states, we need to compute their energies, we need to acknowledge their multiplicities, and then from those two things, multiplicity times Boltzmann factor gives us this statistical weight. The new feature of this problem is this term in the energy, epsilon int. That is where cooperativity is coming from. What that's going to do is it's going to bias the doubly occupied state. It's going to make that state either more favorable or less favorable, depending on if we have positive or negative cooperativity. So I'm basically ready now to write the average number of bound ligands. So average number of bound ligands and that's, and also I can write P0, P1, and P2, which is the probabilities of this empty, the doubly bound, and the singly bound and doubly bound states. So let's do that first. So P0 is given by 1 divided by 1 plus 2 L over omega e to the minus beta delta epsilon plus e to the minus beta delta 2 delta epsilon plus epsilon int. And then the probability of singly bound is L over omega e to the minus beta delta epsilon, and then divided by the same denominator. So let me capture this. Bear with me. So the probability of this state is L over omega squared, and e to the minus 2 beta beta 2 delta epsilon plus epsilon int. So those are the probabilities of the three different categories of states. And let me show you these. So what I'm plotting here is the probabilities of so here is that state, here is this state, and then here is this state. And let me be clear. So here's this state, here's this state, here's that state. So what I'm trying to do is I'm trying to persuade you that we can plot the probability of all three of those categories of states as a function of the concentration of ligand. And I want to make sure that everybody's on board with the intuition. The blue curve says that as I increase the concentration of ligand, well, when I have no ligand, clearly the only state that's going to be occupied is P0, the one where there's no ligand bound. That's clear. But as I increase the amount of ligand, the probability of that state has to go down. In the very large concentration limit, the doubly saturated state is the winner, and so that has to have probability 1. And in between, we have the singly occupied state, which, I did this backwards. Man, what an idiot. I'm so sorry. So, sorry, this is the doubly occupied state here, and this is the singly occupied one. I apologize. I'm not gonna redo the vignette. I made a mistake, and it's par for the course, and I apologize. So at any rate, here's the singly occupied state, this one, and that's the red curve. And then the doubly occupied state is the yellow curve, and like I said, in the large concentration limit, that one has to be the winner. Now, the picture I'm showing on the left has no cooperativity. What I mean by that is we have no epsilon int. On the right, I've now cranked up epsilon int, the interaction energy, and notice what happens. We've basically killed off the singly occupied state. The system basically goes directly from no occupancy all the way to doubly occupied, with hardly any statistical weight attributed to the singly occupied state. And that's the essence of cooperativity, right there. So I really want to drive that point home. Okay, so that's the essence of it. Now I wanted to say one other thing because cooperativity has a really interesting feature with respect to binding curves, and that is that the binding curves exhibit a change in curvature. That's often referred to as having a sigmoidal behavior, which you can see clearly here. So this curve, it starts like this with a positive curvature, and it ends with a negative curvature. That means that the curvature has to change signs at some point. So that's one way of thinking about it. So when we talk about cooperativity, we are going to talk about it from a number of different perspectives. One of the perspectives is that we could say, well, we could fit the binding curve, this thing, according to a Hill function. That's what I show you here. And if the Hill coefficient n is greater than 1, then we say that's cooperative binding. So that's one way. We're going to hold all these different ways of thinking about cooperativity in our minds at once. The second way of thinking about it has to do with the slope at the midpoint. So if I have a steeper slope at the midpoint, this thing is behaving more like a switch. In fact, this is part of the logic, I would say, of why cooperativity is so common in biological systems. And that is because many times we want a switch-like behavior, like in the binding of oxygen by our hemoglobin molecules. I take a deep breath, I saturate my tetrameric hemoglobin molecules, there's 4 binding sites, and I do so in a way that's cooperative, meaning that I grab lots of oxygens, and then when I get out to the tissues, lots of the oxygen is delivered. In other words, we're not just on this red curve, we get a much more switch-like behavior. And then, as I already mentioned, there's this notion of the change in curvature at the midpoint. That's another way of signifying that we have cooperativity in the system. So what have we done? We worked out the states and weights for this cooperative binding. We acknowledge the binding probability. I could also, as I said before, I could write the average number bound. Average number bound. And that's equal to 0 times P0 plus 1 times P1 plus 2 times P2. And actually, I need to multiply by 2 because there's 2 of these states. Okay, good. So let's just be pedantic and write that out. So I know that that's going to be. I can grab this thing. That's going to be average number bound is going to be given by this. But there's 2 here. And then I also need to add 2 L over omega e to the minus beta delta epsilon. So that's the average number bound. It's a bit messy, and I apologize. Let me make a point. And the point is that the Hill function is the limit where epsilon int dominates, if you like. And in that point, average n bound is going to be equal to, for our case here, it's going to be equal to 2. And then I'm going to write it a little bit more provocatively now. Like that. The average number bound is going to be of this functional form, which is what I showed you at the bottom. This is just a first introduction to Hill functions. I mainly have a bad vibe about Hill functions, which I'll probably give a little bit of a discussion of at some later point. For the moment, I want to just say it's a convenient representation of sigmoidal binding, and so we'll find it convenient to use, but to me it's always should be thought of as the limit of this better expression, which I show you here, which is the ratio of these 2 polynomials, and that's the more, let's call it, honest treatment of cooperative binding. So that's all that I have to say about this for the moment. We're going to invoke these ideas regularly from here on.